So let's now look at the molecular orbital diagram for an octahedral complex. Okay, and so this is going to be an octahedral complex that only has a sigma bond. I'll get into what I mean by that in just a second. But first, let's look at the metal bonding side. So we know for any transition metal that we're going to have d orbitals involved, right? And that in octahedral symmetry, those are going to have EG symmetry and T2G symmetry, which went through that. We're going to have the corresponding s orbital involved and the corresponding p orbitals involved. So pretend, for instance, that we are in a first row transition metal. This is a generic diagram that I've written. We'd be talking about the 3d orbitals right here, the 4s orbitals here, and the 4p orbital right here. So one thing first that you might be wondering is, okay, if I look at the periodic table, I know that the ordering of the ordering of the orbitals is not what you have right here in terms of energy, right? So let's look at the periodic table. So if we look at this periodic table, let's say we're some 3D element, right? Okay, well, to get to a 3D element, I'm going to go 4s is lower in energy, then 3D, then 4D. Okay, but that's not what I have written here, right? Sorry, then 3D, I should say. So 4s, 3D, I said 4D. 4s, 3D, 4p, right? Just going across. We know that from general chemistry. That's not the order I have right here, right? I have 3D, 4s, 4p. So in other words, based on our periodic table kind of knowledge, we would think that this s should be down here. Okay, why is it not? Well, there's nothing wrong with the periodic table. This is correct. Okay, but these, when we talk about the periodic table, we're talking about neutral elements. Okay, now most of the time when we're talking about complexes, we're usually talking about cations. Okay, most complexes are cationic, and because of that, when you've or there's some electron density away from the metal, okay, that's being pulled away from the metal relative to when it's a neutral element and making a bunch of metallic bonds to one another, like a bulk piece of iron, right? That has a very different electron configuration from complexes here, and the energy actually does this flipping. Okay, so the 3D actually changes. Okay, and this has to do with effective nuclear charge and electron penetration and things that we talked about way back in chapter 1. Your effective nuclear charge increases, okay, when you are talking about when you're talking about a cation, right? Because you have removed some electrons, so they're less shielded. And remember how your p orbitals could penetrate more than your s orbitals. Well, your d orbitals can penetrate more too. So they're going to be more sensitive to this effective nuclear charge, and that causes them to go lower in energy and causes this flip. All right. So that's just a little bit about this side. Okay, this is the metal, right? These are the 6 ligands on this side. And so just like in any MO diagram, right, we start with what we have, okay, in the atom and on the atoms, and then we're going to make the molecule together by combining, making bonding interactions and anti-bonding interactions. So what do we have on the ligand? Well, here I've shown 12 electrons. And the way you can think about that is, right, some ligand with a lone pair, and there's 6 of them. And they're going to be donating in and making a bond, right? They're going to be making an ML bond. So that's what I mean by a sigma bond. Remember, we define a sigma bond as meaning one set of lobes on each atom overlapping, and that still applies true here, but in a very simplistic way, you can think about it as just like a lone pair on the ligand that's going to go in, attack the metal, right? It's like a Lewis base, Lewis acid relationship, and it's going to make an ML single bond. So that's why I have 12 electrons here, because we basically have, 6 sets of lone pairs. We're thinking about it like that in this way. Now, you can also have pi bonding in metal complexes, and we'll go over that a little bit later in this chapter, okay? Right now, we're just keeping things simple, thinking about sigma bonding. So when you have sigma bonding, it turns out you have to then, you have this directional bonding, right? That's occurring now from all of these in an octahedral fashion, right? So you have to have orbitals that have the correct symmetry to accommodate for that. And there's group theory methodology called SALT, symmetry adapted linear combinations. We're not going to get into that in this course. But there's some methodology that allows you to calculate what the symmetry of these orbitals are. And in this case, I'm just telling you, okay, it's A1G, EG, and T1U. We can do a little bit of check work right here. You may remember from Mulliken symbols in character tables that the A1G symbol is singly degenerate, okay? That the EG Mulliken symbol is doubly degenerate, meaning there's two of them, and the T1U is going to be triply degenerate. That's what the symbols A, E, and T stand for. And so that's a total of 6 orbitals for the 6 ligands that we're talking about that are forming sigma bonds. So you can look at a character table to see about these more in depth, but you know, for the purposes of this course, we don't have to worry about it. So these 12 electrons are, if we have right now what I've drawn is a D0 complex. I haven't put any metals, any electrons on the metal, right? But these 12 electrons on the ligand are going to go down here and populate these smallest, lowest energy orbitals, right? And so you can see, right, an A1G went mixed with this S orbital to make a bonding and an anti-bonding. 3 of the T1Us made a bonding and an anti-bonding. And then the EG came and made a bonding and an anti-bonding. And then what was left? Well, you used up the A1Gs, we talked about the EGs and the T1Us. So those are these, and these. Left was T2Gs. So T2Gs have to then therefore be non-bonding. Nothing can bond with them. So they just slide over. And so this portion, okay, that's what we're talking about when we've been talking about crystal field theory. We've been just honing in on one part of the molecular orbital diagram, which is the ones that are associated with the d orbitals, okay? But really, now we have like the bigger picture of it in terms of the MO diagram, which is, we know is a better reflection of reality, right? Now we're making this transition from crystal field theory to MO theory, which is rooted in quantum mechanics. Crystal field theory is not, it's just a simple electrostatic idea. And so now we have this better context where we can know that this is a non-bonding, okay, MO, these T2Gs, and this EG is actually the anti-bonding. And this gap here is what we defined earlier as in crystal field theory as delta O, or also 10dq, right? We just gave it a different name. It was also 10dq. All right, so here's what's kind of interesting. The non-bonding orbitals are right here. These EGs are like the repulsive sort of orbitals where there's a lot of interaction between the ligands. Now we don't have this repulsive idea. This is just naturally came out of the MO theory. This is just an anti-bonding orbital. Okay, so it's not like a lot nicer this way. And something else that's very interesting here is that if we add 6 electrons here, okay, that gets us to 18 total electrons. Okay. If we add a 19th electron, then we start going into anti-bonding orbital. And generally, when you're looking at an MO diagram, if you have to put electrons in anti-bonding orbitals, you know, that's usually not favorable. If you don't have to do that, that's good, okay? And so we have this sort of principle now that we've come up with by looking at this MO diagram, that if you have 18 electrons, that should be particularly stable because you have a certain number of electrons that doesn't fill any anti-bonding orbitals. And if we look at the periodic table now again, this is sort of the transition metal equivalent of the octet rule. Instead, we have an 18 electron rule. Because look, right, if you go from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13, 14, 15, 16, 17, 18, you got to a noble gas configuration, right? So there is the equivalent of the octet rule for transition metals. As we'll see, there's a lot of exceptions to the 18 electron rule, but what we're going to do in the next video is talk about the 18 electron rule in depth, just like these exceptions to the octet rule, right?